What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about strengths of acids and bases and what actually influences their strength, as well as the structure of those and how that influences them being either a strong or weak acid or base. So, there are two things that influence the strength of acids and bases, and they all distill down to ionization. So, one of the biggest things you have to realize is that the thing that makes a strong acid or a strong base, it's its ability to ionize, which means its ability to just break apart. Because if it's more able, or if it has a higher ability to break apart, then it is a stronger acid and stronger base. There's two things that influence ionization. There is one, the strength of the H and the hydrogen bond paired with whatever base or whatever we're talking about. So the strength of our H to X bond. X is just representing whatever our molecule is. And most things that I'm going to be talking about really applies to acids, but it still applies to bases as well. But more of the examples will apply to acids, but it still matters that the strength of the hydrogen bond really dictates how strong that acid or base is. So in these examples, I'm really going to focus on acids since that hydrogen bond really applies to acids, that strength. But these applications still apply to bases because a strong base is characterized by its ability to ionize much easily. So the strength of the hydrogen bond. Now, what do I mean by this? Well, a stronger bond means it's harder to break up. So the strength of the hydrogen bond really dictates if it's a strong or weak acid. So let's just say we have a high strength. So if we have a high strength of the H bond, so let's just say high strength of H bond, the hydrogen bond. If there's a lot of strength between the hydrogen bond, then it's going to be a weak acid. So I'll put weak acid. And you might be wondering, well, why is it a weak acid? Well, like we talked about, and I'll actually write this down just for remembering that a strong acid ionizes, and I'll just put ionizes the most or fully, ionizes even completely, so ionizes. And knowing this, we can understand that if we have a strong bond between a hydrogen and let's say a fluorine, it's going to be really hard to pull them apart, and that's why it becomes a weak acid. For example, and we're actually going to go through that example right now. So we have hydrofluoric acid. I really don't know. I'll just say HF. So we have HF, and let's just say we also have HBr, HCl, and HI. So pause this video and see if you can actually classify which one is a stronger acid, which one is a weak acid, and try to rank them. All right, so if you did end up ranking them, then you'd see that it would be something like this. So we'd have arrows like that and something like this. So if we were to rank them, then we'd say that the HI is the strongest acid out of all these other acids. And you might be wondering, well, why is that? Well, if we look at our periodic table, we know it goes from fluorine to chlorine to bromine to iodide or iodine. So this HF over here is going to have the highest ionization energy. And ionization energy is the energy necessary to break those bonds. So if we have a high ionization energy, that means we have to have a lot of energy to break those bonds. And since we need so much energy to break those bonds, it's going to be hard to break this HF acid over here compared to the HI because there's so much energy that's needed to break that bond. And if you remember from periodic trends, anytime I think it's hydrofluoric acid, the hydrofluoric acid is going to have one of the strongest ionization energies because when you move from left to right and from down to up, you're going to have a higher ionization energy. So Remember, if we have high ionization energy, we're going to have a weak acid because we need more energy to break those bonds. And going down the periodic table, we go from fluorine to chlorine to bromine to iodine. So we're going from a high to low ionization energy, and this is why this HI over here is a strong acid. Now, HCl, HBr, they're still strong acids, but HI over here is the strongest acid out of all of these because it has the lowest ionization energy. Now let's look at the second qualification of what influences ionization, and the second one is polarity. So polarity, more specifically the polarity of our HX bond. Since we're mostly talking about acids in this video, which these principles still apply to bases, but we really want to focus on acids. So what do I mean by polarity? Even what is polarity? Well, polarity is basically the imbalance of charges. And when you have a high polarity, you're going to have a stronger acid. So when we're talking about polarity, it's this difference in electrical charge. So we could say maybe hydrogen over here has a plus charge, and we have some sort of molecule X has a minus charge. So if we have a large disparity in this electronegativity, if we have a large polarity, then it's going to be easier to break that acid up and to ionize that acid. If we have a high electronegativity, this is going to result in a higher ionization. This is going to result in a stronger acid. Because with this HX molecule, we can ionize it more easily to hydrogen plus and whatever X minus might be, those ions. So if we have high electronegativity, just remember we'll have a larger ionization, and that results in a stronger acid. So if that still sounds confusing, let's actually illustrate it by talking about oxo acids. So oxo acids are just acids that contain a hydrogen, oxygen, and a central non-metal atom. So central non-metal atom. So an example of this will be something like HClO3, for example. And if we draw that Lewis structure, it would be something like this. So we'd have two oxygen electrons over there. Then we have Cl plus over there, oxygen over here, and we have our other Cl, or excuse me, this other O, the other oxygen, and this is HClO3. And this is an oxo acid because we have hydrogens, we have oxygens, and we have, oh, I forgot to put Cl right there. Our Cl is our central non-metal atom. So this is what an oxo acid looks like. And let's compare it to another oxo acid to illustrate polarity and really give you a sense of how an increase in polarity results in a stronger acid. So I'm just gonna just copy paste this thing since I only have to add Br in the middle, or bromine in the middle, and this would result in HBrO3. So when we're looking at this sort of molecule, we really want to first look at our oxidation numbers, because oxidation numbers, and we'll actually talk about how they influence the strength of an acid. So over here, our oxidation number is 1, 2, 3, 4, 5. And we could determine our oxidation numbers by just looking at how many electrons are around there, or we could just look at our chemical formula and know that oxygen is a -2, hydrogen is a +1. So 6, this would be -6 plus 1 is -5. So to make it a neutral atom, we need to make this a +5. And same thing over here, -2 plus 1, since Br and since bromine and chlorine are in the same group, then this is just going to be +5 as well. So we have the same amount of oxidation numbers, but here's the thing. Chlorine is much more electronegative than bromine. So I'll write this over here, and let me actually change the color just to emphasize this point. Chlorine is more electronegative is more electronegative than bromine. And why is this? So electronegativity follows the periodic trend from left to right, where we see an increase of electronegativity going all the way to fluorine, and we also see an increase in electronegativity from down to up. So going from Br or iodine all the way to fluorine. So we're going to have a higher electronegativity with the Cl, and that is why this HClO3 is a stronger acid because it has the most electronegativity. And just to illustrate this even further, here's what I mean by electronegativity. So over here, and I'll just highlight this chlorine over here. So chlorine over here is more electronegative. And being electronegative means that you're pretty much wanting to take all the electrons. You are a selfish element that wants to take all the electrons. That is what electronegativity pretty much is. Just like in water, oxygen is the most electronegative because it's pulling those hydrogens to itself. It's pulling the electrons from the hydrogens. So this is the same thing chlorine is doing. It is pulling those electrons around its sort of arena, I guess you could say, and it is a stronger acid because it can lose this hydrogen much easily. Because all it wants to do is take these electrons that's next to it. What's next to electrons of the chlorine? Well, we have electrons from this oxygen, this oxygen, this oxygen. So it's going to pull those electrons, and we really don't even need this hydrogen. It's already taking all these electrons over here that this bond between hydrogen and oxygen can be ionized much easily because this oxygen pretty much is attracted to the chlorine. This oxygen is attracted to the chlorine. This oxygen is attracted to the chlorine. It's not attracted to that hydrogen anymore, and that's why it can lose it much easily. This bond over here, so let me actually write it down. This ClOH over here, this hydrogen is pretty much acting as a third wheel because this oxygen is much more attracted to the chlorine. The chlorine is much more electronegative. The Cl is attracting the oxygen and it can dispense that hydrogen as it pleases. So bromine can still lose that hydrogen, but not to its fullest potential as chlorine can, because bromine has a lower electronegativity, so it's still trying to pull these oxygens towards itself, but will still have that hydrogen. It's not going to be fully ionized because this bromine just doesn't have as much strength and power as this chlorine has in pulling electrons. So we can still keep this hydrogen, and that's why bromine, this HBrO3 compared to HClO3, this is much more of a weaker acid because we cannot ionize this bond over here of that hydrogen much easily compared to the bond over here with that hydrogen and oxygen. When we have a high polarity, when we have a high difference in electronegativity, then we're going to have a stronger acid because it can break apart easily. These hydrogens can break apart from the molecule, and this, just to illustrate, would produce ClO3 minus, and this would produce BrO3 minus. So that is illustrating polarity and how it can influence the strength of an acid. All right, so going back to those oxidation numbers, and we talked about how oxidation numbers could actually influence the strength of an acid. So let's just write over here. And oxidation numbers, so I'll just put a higher oxidation number. So higher oxidation number, which we're actually saying more positive. So if we're going from maybe -5 to -4, that's still a higher oxidation number because it's becoming more positive. So if we have a higher oxidation number, then this is going to become a stronger acid. Stronger acid. And why is this? Well, it's because electronegativity increases as the oxidation numbers increase. So I'll just put electronegativity. So electronegativity increases as the oxidation numbers increase. And that's something that you really have to know. And some examples of this would be, let's just do a white color right there. And this would be something like HClO4, then HClO3, then HClO2, or let me put Q right there, NHClO. So if we label the oxidation numbers, we're going to have a -2 over here. This is going to be -8, +1 over here. That is going to be a +7. So we already have a really pretty high oxidation number. Then over here, -6 +1. This is going to be +5 because this is going to add up to +6. This is going to add up to -6. So same thing over here, but this is going to be -4 +1. That's going to be +3, and -2 +1 and +1. So as you can see, we have a stronger acid of HClO4 because we have a high oxidation number over here. So this is actually one key thing I'd highlight, and something that you guys should definitely memorize is that a high actually let me change the highlighting. Let me just box this real quick. So a high electronegativity is going to correlate with a high oxidation number. Or if we have more oxidation numbers, if we have a higher oxidation number, which means more positive, then we're going to have more electronegativity. And we know that more electronegativity is going to be a stronger acid because that hydrogen can ionize much easily to produce, for this example, it would be ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. So remember that higher oxidation numbers mean higher electronegativity. Alright, so now this is going to be practice for you guys. And for this practice, we're going to look at carboxylic acid. So carboxylic acid. And carboxylic acid is basically having this sort of acid molecule, whatever that might be. So I'll put acid M just to say acid molecule. But we're going to have a carboxyl group, and this is what makes it a carboxylic acid, because carboxyl is our COOH sort of formation. So just do a carbon in the middle. Then we have a oxygen double bonded to that carbon. Then we have oxygen over here, and we have hydrogen. And this is our carboxylic group. So that's COOH, and I think that's minus charge. So that's our carboxyl group. Our conjugate base would be this acid molecule and COO minus. Alright, so now that we know that, have a basic understanding of carboxylic acid, now here is the question. So we have hydrogen and we have a carbon, and this is going to be acetic acid. So we're going to have that, CO, and double those electrons, and that's going to go to oxygen and hydrogen. And let me actually organize this just a bit. So we have something like this, and this is just going to be acetic acid. So I'll put acetic acid just to label this. And let's do the same exact thing. So I'm just going to copy paste this. So copy paste. But this time, instead of putting hydrogen on top, there's going to be a chlorine. So, and this is going to be chloroacetic acid. So, chloroacetic acid. So the question that I'm sort of wanting to ask is, which of these acids is stronger, the acetic acid or the chloroacetic acid? And why is, if you pick whichever one, why is that one the strongest one? So pause this video and try to answer that question. So hopefully your answer was the chloroacetic acid. And I'm guessing the reason why you put chloroacetic acid is because there is a chlorine over here. So there's this chlorine. And if we remember the stuff we talked about, polarity and whatnot, this chlorine over here is much more electronegative than this hydrogen. So it's going to pull the electron density towards itself. So the Cl is basically pulling electrons to itself, and we know that when it pulls electrons, it's a higher electronegativity, and this is why it's a stronger acid. So when it's pulling all these electrons, we don't really need this hydrogen anymore, and that's why it'll be able to ionize easily. It'll be able to separate that hydrogen from our sort of compound. And when we're talking about electron density, this is basically sort of, I kind of think of it as the area or the amount of sort of the density of electrons that is circulating around. And if we have something this electronegative as Cl, not only does it stabilize the molecules, but also pulls electrons towards itself. So it's kind of like you could think of it as the center of attention. And this hydrogen over here is going to lose attention from the molecules, and that's why we can lose it much easily. So if we were to draw this as a Lewis structure, then it's going to look something like this, where we have our chloroacetic acid. It's going to lose that hydrogen and turn into a negative charge, and this is our reactants and products. So this is our acid, this is our conjugate base. So that's how we can look at polarity, or we can look at a electronegative atom, or even looking at the oxidation numbers and how that influences the strength of an acid. Because if we have something that has a high electronegativity, then we're obviously going to have a stronger acid, because that acid can ionize much easily. It can lose that electron much easily. Hopefully this video helped you understand the strength of acids and what actually makes them strong. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.